My name is Nasir. I am a student of computer science and in Monroe College, New York. So today I am excited to present my research paper on the topic of review on blockchain for IoT security and data integrity. My co-authors are Mujiba Shaima, Tanvir Islam, Norun MazharulIslam Tushar, Estak Ahmed, Sushanta Shaha, and Sarder Abdulla Al Siam. Moving on. So now the abstract. Actually our abstract was about the rapid advancement of smart technologies. So rapid advancement of technologies has significant bolstered the government capabilities for digital transformation. The integration of these technologies in various government functions. And here, however, blockchain is a distributed ledger technology that makes it possible to record transactions over a network of computers in a safe, transparent, and unchangeable position. The way that blockchain and IoT can enhance each other advantage is how they are connected. Blockchain technology with its decentralized and impenetrable ledgers offers safe and effective storage and transfer of the massive volume of data gathered by the Internet of Things devices. Organizations may guarantee the safety and integrity of IoT data by incorporating blockchain technology into IoT systems. This will allow for reliable and open communications and transactions between users and devices. Here, we summarize the current body of research and draw attention to the main cybersecurity issue facing blockchain-based Internet of Things. These problems are divided into three primary categories: security of IoT devices, security of blockchains, and integration of IoT devices with blockchain network. To further address a little about these issues and improve the cybersecurity of blockchain-based IoT systems, we also analyze future research directions. Moving on. Before going to the introduction, we actually use some keywords here like IoT, blockchain, blockchain layers, hash identifications. See, in the introduction, the emergence of Internet of Things has revolutionized connectivity and data exchange since the conceptualization by Athon and Gamble in 1999. This paradigm shift has led to its widespread adoption across various industries, promising enhanced efficiency and evidence through interconnected devices and networks. But as IoT ecosystem have grown exponentially, so have the security device issues that threaten the security and confidentiality of the data shared across these networks. Fundamentally, sensors integrated in devices that gather and send data to central servers or cloud computing center enable data sharing and analysis in the Internet of Things. This connectivity creates dangers like data extraction challenges and privacy violations, even if it is present until unheard of change for automation and creativity. The need of addressing such safety concern is increased by the forecast growth of the IoT connected devices to over 75 billion in the near future. At the heart of the IoT ecosystem lie fundamental components such as sensors, computing, nodes, and devices working together within a multi-layered framework encompassing the business, application, network, and physical sensor layers. Modern Internet of Things network, despite their sophisticated characteristics, have trouble allocating resources effectively and upholding strong security protocols, especially in the face of constantly changing cyber threats. The concept of massive IoT further complicates the security landscapes by envisioning network supports billions of connected devices, enabling innovative applications such as telepresence, autonomous driving, and biosensors. However, the sheer scale and diversity of IoT network amplifies security concerns and underscoring the need for proactive cybersecurity measures. In response to these challenges, emerging approaches seek to integrate cognitive technologies like artificial intelligence and machine learning with IoT environments, enhancing device capabilities and strengthening security protocols. Furthermore, trust management and data immutability emerged as crucial consideration, particularly in industries where asset tracking and privacy preservation is paramount. Blockchain technology has emerged as a promising solution to fortify IoT security, leveraging its decentralized architecture, transparency, and cryptographic security to ensure data integrity and privacy. Blockchain-based Internet of Things solution provide a strong fundamental to reduce security risks by decentralizing data storage. However, it improves consensus processes, cryptography methods, and smart contracts. Architecturally, blockchain-based IoT systems consist of distinct layers, including the device, communication, smart contract, and application layers, each serving a unique function of ensure secure and reliable operation. Blockchain-based solutions come with their own set of difficulties that need to be managed even if they have enormous promise to solve cybersecurity issues in Internet of Things systems. Basically, this paper aims to provide a comprehensive review of existing literature on cybersecurity, challenges in blockchain-based IoT system, categorizing challenges into three main categories, and discussing potential solutions and future research directions to advance the cybersecurity of this system. Through rigorous analysis and strategic insights, this paper seeks to contribute to the ongoing discourse surrounding IoT security, fostering innovation and resilience in the face of evolving cybersecurity threats. Moving on. The methodology. The review paper conducted in a systematic way to thoroughly analyze the security and data integrity of blockchains for IoT things. The methodology comprised searching electronic database like PubMed, IEEE Explorer, Science Direct, and Google Scholar for relevant material in depth. Keywords including blockchain, Internet of Things, IoT security, and data integrity were utilized to identify relevant peer-reviewed articles, research papers, conference proceedings, and academic publications published within a specified time frame. Only studies meeting predefined inclusion criteria such as relevant to the research topic and publications in reputable journals or conference proceedings were included. Non-peer reviewed sources, duplicate publications, and opinion pieces were excluded to maintain the integrity of the review. Selected studies were gathered methodically. Then the results were analyzed to reach conclusions on the use of blockchain for data integrity and Internet of Things security. The combined data were examined to find recurring themes, patterns, and gaps in the literature. The findings of the review were then synthesized and reported, providing a comprehensive overview of the current state of research in blockchain for IoT security and data integrity. Moving on. So, what is blockchain technology? After being first presented as an approach to prohibiting people from spending their digital currency more than once, blockchain technology has developed to be used in a variety of industries, including healthcare, logistics, and the Internet of Things. The aforementioned IoT security challenges can potentially be addressed by the blockchain. Blockchain technology can also enhance security and privacy in Internet of Things systems because of its intrinsic advantages, which includes the immutability of append-only chain data, a decentralized and non-changeable ledgers, transparency, and cryptographic security, among others. Several benefits of blockchains contribute to IoT system security, including transparency. Since the blockchain records very transactions and makes it accessible to all users, it is a transparent technology. As a result, hackers find it more difficult to steal information or alter data. Transactions in a centralized system aren't always clear cut, which makes it challenging to find out the people who are committing fraud or altering data. Decentralizations. Blockchain is an example of an decentralized technology, meaning that no single entity controls it. Hackers find it challenging to target and launch an attack because of this. A single point of failure exists in a centralized system since all data is kept on that one server. Since data in a decentralized system is spread across several nodes, hackers have a harder time accessing all the data. Cryptographic methods. Blockchains protects data using cryptographic methods. Algorithms known as cryptographic techniques encrypt data, rendering it unintelligible to unauthorized user. Because of this, hackers have a harder time stealing data from the blockchain. Data is frequently stored in plain text in centralized systems, which facilitate data theft by hackers. And then comes to consensus mechanism. Consensus methods are used by blockchain technology to verify transactions. Consensus methods are algorithms that guarantee that every network members agree that a transaction is valid. Because of this, it is more difficult for hackers to control the network and authorize unauthorized transactions. Since only one party oversees verifying transactions in a centralized system, hackers have an easier time to controlling the systems. And also the smart contracts. The self-executing contracts that are recorded on a blockchain can be made using the blockchain. Hackers have an easier time to control these, although they are irreversible and tamper-proof. Smart contracts allow for automation and the enforcement of agreement between parties. IoT system security and efficiency may increase as a result. Moving on to the blockchain framework. Blockchain-based IoT systems can offer a strong framework for guaranteeing the integrity, privacy, and dependability of IoT data and transaction by implementing these security aspects. To comprehend that architecture and the security elements of blockchain-based Internet of Systems, it is possible to identify multiple levels. These IoT system levels are depicted as follows. At first, the application layer within the on the chip module and cross chain, and is supported by the contract layer, the development environment of a smart contract, and the development languages of a smart contract. And then comes to the consensus layer, where POW class consensus and the BFW class consensus and also CFT class consensus are there. And then the network layer, the network structure, where we can find the network structure, communication mechanism, and encryption mechanism. And finally, the data layer that is consists of data structure, data model, and block storage. So data layer design, data layer designing the data structure, grouping information, and sorting it in blocks are all handled by the data layer. Data cannot be published or changed in the blocks of a blockchain network without a shared consensus process among its numerous nodes. Pointers, which indicates the position of another node, and lists, which show the chain of connected blocks, are the two main parts of the blockchain constructions. And the network layer. Intercommunication between nodes in a network is handled by the network layer by creating a secure P2P environment. To keep the blockchain network functioning, all nodes can locate, connect, synchronize, and spread with one another in the safe P2P environment. The network layer makes sure that the communication between nodes are error-prone. The blockchain layer, the distributed ledger, and the related consensus processes are part of the blockchain layer. So, which is fundamental part of the system in order to guarantee the integrity and immutability of the data recorded on the blockchain. It logs and verifies transactions. Now comes to the consensus layer. Consensus protocols, which are responsible for validating blocks, ordering new blocks according to consensus protocols, and obtaining consensus from all nodes on recently published blocks from the foundation of blockchain architecture. They ensure that all nodes are in synchronizations, and that the network has a uniform power distribution, and that there is only one verified truth originating from the all nodes. And the final one is the contract layer. The basis of blockchain programmable feature is the contract layer. The runtime environment and the programming language for smart contracts are presented in this work. Three selected groups comprises the development language for smart contracts. So the scripted based smart contracts is made up to up-to-date data and instructions. Cellular automate contract language and instructions make up a Turing complete smart contract. One kind of verifiable contract is a smart contract. The contract syntax can be used for data storage and authorization verification, and it resembles LISP in several ways. The data integrity. So data integrity, accountability, transparency, and interoperability can all be enhanced by blockchain-based Internet of Things. IoT system deployment based on blockchain, however, also bring with them particular cybersecurity issues that must be resolved. These difficulties cover topics like integration of IoT devices with the blockchain infrastructure and security concerns with IoT devices and blockchain security. It is essential that these platforms are identified and resolved in order to deploy a blockchain-based IoT system in a secure way. To overcome these obstacles and facilitate the broad deployment of blockchain-based IoT system across several industries, ongoing research and cooperating among diverse stakeholders are required. Our goal is to provide a thorough analysis of the body of research on cybersecurity issues with blockchain-based Internet of Things technologies. The difficulties fall into three primary groups. This area concerns the security of IoT devices, the security of the blockchains, and the integration of blockchain security with IoT devices. We also discuss the shortcomings of current position. Blockchain provides security to IoT through its decentralized and immutable nature. Distributed ledger technology and cryptography are used by blockchain to guarantee the confidentiality and integrity of data transferred between Internet of Things devices. A block which is connected to earlier blocks to form a chain, record each transaction, or data exchange. This decentralized structure eliminates the needs for central authority, reducing the risk for a single point of failure or attack. Furthermore, Enhancing security is the implementation of consensus technique like proof of work or proof of stake, which guarantee that transactions are validated and accepted by the network users. Overall, blockchain enhances the security of IoT ecosystem by providing a transparent, tamper-proof, and decentralized framework for data exchange and transaction verification. Moving to the cryptographic techniques. It consists of encryption, hash functions, and digital signatures. So the encryption is blockchain utilized cryptographic algorithms to encrypt data exchanged between IoT devices, ensuring that it remains confidential and secure. Hash functions. In blockchain technology, each transaction has a separate, a unique cryptographic hash, which act as a digital fingerprint. So any kind of alteration will changes its hash value, therefore altering the network to tempering atoms. Digital signature are used to authenticate the identity of participants in the blockchain network. Each participant has a unique private key used to sign transaction, while public keys are used to verify signatures only. Moving on. Distributed ledger technology. Every node in the decentralized network of nodes that makes a blockchain keeps a copy of the ledgers. Its decentralized structure elements the need for a central authority and makes a single point of failure or assault less likely. By requiring network participants to reach a consensus algorithms like proof of work and proof of stake guarantee that transactions are approved and added to the blockchain. This system keeps the ledger's integrity intact and stops fraudulent transactions. Immutable ledger. A transaction is tamper-proof and unchangeable once it is added to the blockchain. Since the ledger is distributed, changing historical data would require agreement from most nodes, which makes it nearly hard to change previous transaction. And then data recorded on the blockchain is particularly resistant to illegal modification and hacks because of its immutability, which guarantee data integrity. Smart contracts. In blockchain technology, smart contracts are self-executing contracts and predetermined terms and conditions are written by itself. They enforce contracts between parties and automate the execution of transactions. Smart contracts also helps to improve security by removing middlemen and guaranteeing that transactions are carried out by only when certain requirements are satisfied and reduces fraud or manipulation possibilities. Moving forward to the literature review. Sorry. In this section, we'll provide a comprehensive overview of the significant research findings and insights on blockchain security in IoT systems. Basically, we explore the different methodologies, tactics, and frameworks. These approaches that researchers have used to study the possible advantages, difficulties, and use of blockchain technology in protecting IoT devices and networks. In addition, we emphasize the main discoveries, which involves the creation of a structure, procedures, and rules for effective and protected Internet of Things systems based on blockchain technology. We therefore assess performance measurement that includes the ability of handle increasing demands, safeguard personal information, and establish reliability. Lee et al. 2020 conducted a thorough examination of the diverse security concerns that emerged within the framework of blockchain system. The report highlighted the susceptibility of blockchain system to double spending attacks as a significant security concern. Double spending attacks occur when a person intentionally spends the same cryptocurrency twice, resulting in a loss of trust in the system. This analysis focuses on smart contracts, which are contracts that can execute themselves automatically when specific circumstances are fulfilled. Nevertheless, these contracts are susceptible to a multitude of attacks, including code exploits and denial of service attacks. The authors explored many strategies to reduce this risk, including conducting audits and tests on smart contracts to identify weaknesses. The writers emphasize want to additional investigations and advancement in this domain to guarantee the extensive acceptance and efficacy of blockchain technology. This article also conducted an extensive examination of the current security measures and presented solutions aimed at tackling these difficulties, rendering it a significant asset for researchers and professionals working in the domain of blockchain security. In the research work, Dory et al. 2017 investigated the feasibility of utilizing blockchain technology to bolster security and privacy in the realm of Internet of Things devices. The authors provided an analysis of a smart home in which different Internet of Things devices and interconnected engage in communication with one another. They emphasize the security and privacy hazards linked to such gadgets, such as possibility of unauthorized entry and data leaks. This article discussed the obstacles to applying the highest nodes of this system, including the requirement for effective consensus processes and the possibility of higher energy uses. It also explored how blockchain technology greatly improves security and privacy of IoT devices. Islam et al. 2021 conducted a thorough examination of the security concerns and obstacles that blockchain technology encounters. The writers commenced by introducing blockchains and its fundamental characteristics, including decentralizations, immutability, and transparency characteristics. Furthermore, they deliberated on the many forms of assaults that blockchain system may encounter, including 51% attacks, double spending attacks, and smart contracts weakness. In addition, they showcased a range of security protections and approaches, including consensus mechanisms, encryptions, and multi-signature schemes that can be employed to reduce the impact of these assaults. Moving on. Razo et al. 2022 in their research paper used extensive analysis of cybersecurity concerns within the framework of Internet of Things systems based on blockchain technology. There they emphasized the distinct security concerns presented by the IoT devices, such as their constrained computational capabilities and vulnerability of physical assaults. In addition, they deliberated on the prospective advantages of employing blockchain technology to bolster security in IoT systems, such as the capacity to generate tamper-proof records and regulate access to devices and data. In addition, the above authors examined other security measures for example, encryptions, access controls, and intrusion detection that might be employed to bolster security in this system. Sorry. The report presented a comprehensive analysis of different Internet of Things applications that utilize blockchain technology, including smart grids, healthcare, supply chain management. It also examined the distinct security obstacles and potential advantages linked to each application. Blockchain technology guaranteed data integrity. Integrity security systems have characteristics that were defined by the Clark-Wilson paradigm. Properly structured transactions, job separation, audits, authentication, and the principle of least privilege, objective controls, and control over privilege transfers are the part of that make up this system. Hash identification and data divided into blocks. How it's worked. So data from the supply chain is split up into blocks and dispersed among various devices involved in the production chain when it is integrated base framework. In addition to the production data, every block in this data has a unique identification known as the hash and the hash of the block that came before it, which identifies a different portion of the same GXP data. Third-party author. A third-party auditor is someone who has the skills and knowledge necessary to finish each auditing process. We use third-party auditor approach to verify the data integrity. Data integrity is achieved and the data owner is reassured about data security by the third-party auditing architecture they have presented. The owner is aware of every resource available to him on the cloud. As such, data integrity is guaranteed by the approach for all owners of cloud resources. The data owner takes part in the auditing process with this plan. TPA starts by using routine auditing techniques. Any changes that are discovered to the data are sent to the owner. The owner looks over the records of the auditing procedure to confirm those changes. If the owner feels that strange things have been happened with this data, he can decide to have another auditor assigned by him, or he can choose to independently verify his data. As a result, the owner constantly monitor and any modification made to this personal data. The third-party auditor's response cannot go above a given threshold value. The data owner verifies any changes that fall below or are equal to this threshold. If the threshold time exceeds, then the data owner is obliged to perform unforeseen audits once again. The need for a third-party communication channel and the susceptibility to man-in-the-middle attacks are the disadvantages of this approach. Furthermore, the participation of a third party in data processing increases the likelihood of various hackers' risk being implemented. Provable data positions and related methods. Here, a provable data position technique is used to examine statistically the accuracy of the data that is outsourced to cloud storage without requiring the data to be retrieved. The suggested methods is meant to make sure that the server still has the original data so that it doesn't have to be retrieved from the different places. The basis of this model is probabilistic proofs, which demonstrate positions by selecting a group of block and random from the server in order to create a message that the client may use to demonstrate that the server possesses a chain certain blocks, regardless of whether the client has access to it or not. They employ as RSA-based homomorphic verifiable tag. During the pre-processing stage, the user adds metadata and the edits data while simultaneously preserving the client's metadata repository before submitting files to the cloud. The user sends a request to compare the files metadata to the client's metadata library. The request is then sent to the server to confirm that the files saved in the cloud can be changed. In conclusion, the blockchain Internet of Things technologies have great potential, but addressing the related cybersecurity issues will take coordinated effort. We can create safe and dependable blockchain-based Internet of Things systems that spur innovations and revolutionize markets by using a broad and interdisciplinary approach that comprises technological developments, operational best practices, and regulatory frameworks. To encourage people to use blockchain technology, we examine the fundamental layered architecture of blockchain technology, consensus protocols, and a range of application fields. We also document some notable advantages of blockchain's adoption and explain the relationship between the many layers technology and highlighted the technical fundamentals of each layers. So here we put the references where we got this information. So there are 15 total, 15 references I put here in here.